Okay, let us explain that. Now, the way we had it set up, we had the simulation set up. The vertical displacement, which is d sub y, is equal to minus 4.9 meters. That corresponded to t equal 1.0 seconds. The horizontal displacement, d sub x, is equal to whatever initial velocity along the x we gave it, whatever was called here as initial speed, times the time. In this case, the time is 1 second. So whatever that initial velocity was, we multiplied it by 1 second and we got the horizontal displacement. That was called range here. Now the vertical displacement, the 4.9, come out from the fact that d sub y is equal to 1/2 of a sub y t squared plus vi sub y, the initial velocity along the y, times t. But since we are launching our projectile horizontally, our initial velocity along the y is 0. So that makes our equation as simply the first term. d sub y is equal to 1/2 of a sub y t squared. And a sub y, since our projectile is in free fall, we are ignoring air resistance. We didn't check the air resistance here. Now, in that case, my acceleration along the y is going to be just minus 9.8 meters per second squared. Now, if you plug in minus 9.8 here for a sub y, and plug in 1 second for t, you'll get minus 4.9 meters, the way we have observed in the simulation. Now, that vertical displacement is going to be the same no matter what the initial horizontal velocity is. If it is small or large, my vertical displacement is going to still be minus 4.9 meters for that second. The issue is the ability to find a range where, when my projectile falls for 1 second, it's going to reach ground. That's very difficult to acquire. Actually, if you think about the shape of the Earth, and of course this is not an accurate shape, and the people and the tree and the apple here are very much out of proportion. Now, whatever I'm going to draw is going to still be out of proportion, but bear with me, please. So, if I'm going to shoot an object here, horizontally is going to make it tangent to that circle. Now, what we have established with the simulation and with the calculations we just made, no matter what this velocity is, after 1 second, my projectile is going to fall 4.9 meters. The vertical displacement of my projectile is going to be minus 4.9 meters. Now, what if the curvature of the Earth is such that, like the way I drew it here, after 4.9 meters, my object is still at the same height from the Earth as it was before? If that's the case, then my object here is going to still be moving with that same horizontal velocity that we gave it. and after another second, it's going to fall another 4.9 meters, landing here with that same initial velocity. And after 1 second, it's going to fall again 4.9 meters, landing here with that same initial velocity, and so on, making a full orbit around the Earth. That's the principle of a projectile. So what we are saying here, there is a particular initial velocity that we can give our projectile such that for the position from where we are going to launch our projectile, for example, from this height here, after falling 1 second, our projectile is going to remain at the same height above ground. That's because of the curvature of the Earth. If that's the case, then my projectile is going to remain in orbit around the Earth. Of course, if we give it less than that velocity, the projectile is going to fall short and is going to hit the ground. If we give it a higher velocity, we are going to get a different orbit than a circular orbit, and that's beyond the scope of this course. So the bottom line, the conclusion that we are trying to get from here, for a particular height from which we are going to launch our object, we can find a particular initial velocity. When given that particular initial velocity, our projectile is going to fall 4.9 meters after 1 second, but still remain at the same height relative to the Earth. By remaining at the same height relative to the Earth, it's going to remain in orbit around the Earth.